I recently built this radio-controlled vertical takeoff and landing aircraft, which is optimised to be stable and efficient at model scale. But I've always wanted to build a model that looks and flies just like the real full-scale V-22 Osprey. This video is sponsored by Brilliant. More on them later. The full-scale Osprey is essentially a plane with a helicopter on each wingtip, which gives it the required control during a hover. Fortunately, we have access to both model helicopters and model planes, so all I need to do is merge the two together, just like the real thing. A few people have achieved this in the past by heavily modifying off-the-shelf helicopter designs, which is very impressive to squeeze all the mechanical components of a helicopter into such a small space. And whilst I admire the work that goes into such a setup, the cost and weight of the helicopter components are hard to justify for this project. Some smaller models have a cheat solution where by hiding a small ducted fan in the rear of the fuselage, they remove the need for helicopter rotor heads for pitch control when hovering. But this isn't ideal, as when on the ground, the large hole in the fuselage is obvious, and it makes a loud screaming noise when hovering. My previous VTOL plane controlled the pitch axis during a hover by tilting the motors back and forth, which works great, but it will look very odd to have the huge Osprey engine nacelles tilting rapidly back and forth. So here is my plan. A few years ago I built my own model helicopter, which used a 3D printed rotor head and some interesting electronics. The rotor head was very simple and didn't require all the complex linkage mechanisms of a conventional helicopter, which saved on weight and cost. The way it works is each blade is attached to a hinge, which is free to move, and has no mechanical parts to control it. But because of the angle of the hinges, if the blade swings back and forth, the angle of attack of the blade will change. And this blade pitch angle is reversed on the opposite blade. Now because the blades are free to rotate about each hinge, the way we control the blade pitch is done by varying the motor speed. For example, if the motor applies power in this direction to increase in RPM, both blades would lag behind slightly, creating a high angle of attack on one side and a low angle of attack on the other. And this would also happen if we rapidly applied a brake to the motor, but the blade pitch change would be reversed. Now the difficulty arises when we realise a helicopter adjusts its blade pitch every rotation of the rotor head. So say we want more lift on one side and less on the other, the motor will need to accelerate for half the rotation and then decelerate for the other half, causing the blades to swing back and forth, which could be up to 80 times per second. The way we achieve this motor control is by measuring the motor angle with a magnetic encoder attached to the bottom of the motor shaft. Then with a bit of code we can multiply the desired pitch input by the sine of the motor angle, which applies a sine wave to the throttle output. And with the rotor head attached, it's clear that the blade pitch is greater on one side than the other. Now when I built the previous helicopter, I crashed it quite a few times before I could get it to work. But with this project, I'd prefer it didn't crash at all. So I've built a test rig that allows the motor and rotor head to pivot in one axis. And so far it seems to be working well. Especially in slow motion, it's very clear that the blades create a greater angle of attack on one side than the other. But there's something missing from this setup. The real Osprey has 3 blades on each rotor, not 2. So I 3D printed a 3-bladed rotor head with 2 blades using the same hinge angle, and the remaining blade using the reversed hinge angle, which is the advantage of having a test rig, so I can trial these things without consequences. But surprisingly, the 3-bladed rotor head works just as well. From the slow-mo, it does look like sometimes the blades are at the wrong angle when passing the midpoint, but for the majority of the rotation, the blades are performing the correct pitch angle, resulting in the lever tilting to the left. The next step is to modify the test rig to see how this rotor will control the pitch axis of the aircraft when hovering. This is done by mounting an accelerometer and gyro unit to the arm, and seeing how precise the movement is. Then we can add some weights to the arms to increase its inertia to closer simulate the large fuselage of an Osprey rotating back and forth. Whilst it seems to have decent control authority, with the extra inertia of the weighted arm, it's very clear from the slow-mo that these lightweight plastic helicopter blades are struggling a bit. So I ordered some blades which are similar in size, but are designed for a more aerobatic helicopter, meaning they are far more rigid. This gave the rotor head far more control, but sometimes when making one component stronger, another component will end up failing.
That might be a bit of a problem. Oops.
I then redesigned the hub of the rotor head to be cut from aluminium, as well as beefing up the rotor hinges to hopefully prevent this catastrophic failure from happening again. And now, not only was the rotor head probably less likely to explode, but it also seemed to perform better. So we've essentially built one of these radio controlled helicopters for a fraction of the cost and complexity, whilst also saving weight. Before building the scale portions of the aircraft that will make it look like the real Osprey, we first need to build an internal structural frame. And like my previous VTOL aircraft, I'll be using glass reinforced plastic sheets, as they're easy to cut the required parts from, and these are then attached together using 3D printed brackets. I chose to use 2mm thick sheets for this build because I need the frame to be quite strong to take as much load off of the final fuselage, hopefully keeping the weight as low as possible. The next step is to build the motor mounts and tilt mechanisms, which consist of some fiberglass sheets and a large servo to tilt the motor for transition. This is then mounted on the wing spar with a simple friction fit, and the servo can control the motor tilt with a small push rod. Like with my last VTOL aircraft, I'm using an Arduino based flight controller that runs a custom code called Dreamflight, with a 4-in-1 motor controller and a standard RC 5V regulator to power the servos. It was then time to solder up the motor wires and connect the servos before testing everything worked as it should. I then mounted the rotor head to one of the motors and fixed the aircraft to the table with some weights, so we can see if the rotor head is performing the same as it did on the test rig. And it seems to be wanting to tilt the craft back and forth, so it's time for an actual test flight. Not quite what I'd hoped for, but after a bit of tuning it seemed to look a little promising. And now we've taken a few steps back. Basically what's happening is the flight controller is shutting down, causing everything to restart. But it's occurring randomly, so I can't figure out exactly what the cause is. Anyway, it turned out to be the 3V regulator on the flight controller board, which was evident using the thermal camera. So to fix it, I added an external voltage regulator, and the issue was solved. But then I noticed an odd vibration that would suddenly appear and then get so violent that the aircraft would suddenly drop out of the air. My theory was that the blade RPM was reaching a resonant frequency with the wing spar, so I added some nylon string to try and stiffen the frame. But unfortunately this didn't help much. So I then added some extra carbon fibre braces, which made a significant improvement, and it was finally able to get off the ground and into a hover. Though it was obvious the vibrations were still there. I tried balancing the rotor head and blades as much as possible, which did make a small difference, but it's not completely gone yet. So my next theory was that the motor mounts are flexing, or there is play in the hinges. So I've 3D printed these much shorter and stronger motor mounts, which clamp directly to the wing spar. This does however mean it won't have yaw control, but if it's able to hover, I'll know what the issue was. Despite the rotation to the right due to the lack of yaw control, these vibrations seem to have completely gone. So I manually twisted the motor mounts to hopefully cancel out the rotation, and finally we're getting somewhere. The pitch control with the 3D printed rotor heads works surprisingly well, and the motors stay nice and cool. All it needs now is a stronger wing spar and a completely redesigned motor tilt mechanism. This may look similar to the previous design, but it's got a few major improvements. The most obvious being the new herringbone gear system to tilt the motor, which removes the play from the old push rod. Also, these cheap servos aren't the most precise, but have about 300 degrees of travel, so it's geared with a 3:1 ratio as we only need the tilt mechanism to tilt about 100 degrees. To remove the play in the hinge, I've chosen to use 3 small bearings, which can be tensioned to fit the shaft, which is not only lighter than a single larger bearing, but also these shafts aren't precision machined, so finding a large bearing to fit was near impossible. There is still some flex in this portion of the frame, but it's exaggerated a lot when on the ground as the motors bounce back and forth, so I might reinforce it at a later date. But for now, it's time for another test flight. Finally, it's flying without any braces on the wing spar, and the complete motor tilt mechanisms attached. And surprisingly, it feels quite stable even on this windy day. It's also quite manoeuvrable, but to reduce vibrations, I've put a limit on how much the flight controller can vary the motor speeds. So in extreme control situations, or with a huge gust of wind, it struggles to return to level. Having said that, I probably won't be flying as extreme hovering manoeuvres once the large fuselage is built. Speaking of the fuselage, I'll be building it in the next video using some interesting 3D printing techniques, just like I did with the 3D printed wing in my last VTOL video. So stay tuned for that. Now, as you can imagine, this aircraft needs to be balanced perfectly to prevent the motors getting warm. And to learn about centre of mass and weight adjustments, I highly recommend this scientific thinking course on brilliant.org, which covers how the position of different weights can be moved along a rod to adjust the balance point. The interactive experiments are excellent for understanding the physics, and the questions really test how well you know the theory. And if you get a question wrong, Brilliant provide an excellent explanation to help you learn to improve. Brilliant is the best way to learn math and science interactively, and they have thousands of lessons with exclusive new content added monthly. From physics of the everyday to computer science fundamentals, to learning algebra through puzzles. It's been a while since I graduated university, so using these Brilliant courses to refresh my knowledge on various science topics has been really useful when creating these engineering YouTube videos. Even just a little bit every day can have a huge impact. So go get started for free, or the first 200 people that sign up via brilliant.org/Tom Stanton will get 20% off a premium annual membership. The link will be down in the description below. Thank you very much for watching this video, and I'll see you in part 2. Goodbye.